You'll recall that last time we were dealing with group orbitals, we constructed them for planar CH3, and then through systematic distortions we made pyramidal CH3. And once we had constructed them and we identified, let's see, sigma type orbital, two degenerate pi type orbitals, and then the sigma out orbital, which is even more projected out toward where something might be to bond. And then we use these two parts of our sort of Walsh orbital diagram to make some conclusions just based on counting electrons with the geometric structures of BH3 versus NH3. And recall that BH3 with only 6 valence electrons, if you put it represented in blue here, if you make it planar, those electrons are lower in energy than they are if you make it pyramidal. So when we go from planar to pyramidal, we get slightly worse overlap between the p orbital on carbon and the s orbitals on hydrogen, and that increases our energy by a greater amount than the lowest sigma orbital is stabilized. So, all things being equal, BH3 is planar. That's exactly what valence bond theory and VSEPR give you. In contrast, ammonia, which has 8 valence electrons, same exact number of atoms, so we can use the same orbitals and just compare the two geometries. And here I'm representing the additional 2 electrons of ammonia in red. If we were planar, those electrons would be held in a p orbital with 0 CH overlap. But if we make ammonia pyramidal, those electrons get to be in the sigma out orbital, where there is overlap between the orbital on carbon and the s orbitals on hydrogen. And there's also more s character than you would have gotten in the original p orbital. So it's more favorable for those electrons to be here. So simply based on counting electrons with this picture of orbitals, we can tell we can predict totally what the geometry should be. Okay, good there?
Yeah. I was thinking 351, and I got the question about where the lone pairs of electrons on the molecule ammonia is. Normally, from valence shell electron portion, we know that they're actually in the xp3.
Right.
Okay.
Yeah, and that's if you squint your eyes and forget that the hydrogens are involved, this looks a lot like an sp3 orbital. So that turns out to be close enough for most of what you need to do in 351. Okay, other questions? So I kind of want to hop back and forth between here and Gaussian, but it's not as convenient to do. So we're going to, later today, we're going to take these 4 orbitals from pyramidal CH3, and we're going to combine them together to make ethane. And then I'll show you what those orbitals actually look like as calculated. But before we do that, there's another sort of important geometry that we tend to deal with in OChem, and that is CH2. It could be linear. That is, and again, we're not saying really anything about how many electrons are here, or it could be bent. Okay, so constructing these orbitals, we'll go ahead and start with the end in mind with our energy diagram. I'm sorry my penmanship is not that great when I'm drawing in front of you. I don't know whether it's some kind of up in front of you anxiety or we're just trying to go quickly. But anyway, again, the orbitals that are available to us are the 2s, the 2px, the 2py, and the 2pz. On hydrogens, we've got 1s orbitals each. And then let's just remind ourselves of our coordinate system. Z is here, Y is here, X is up. So in our linear CH2, our molecules lined up in the along the X axis. Okay, so you might imagine that the lowest energy combination would be the one that derives from the 2s orbital on carbon and then the 1s orbitals on hydrogen. Let's see. And then there would be a higher energy anti-bonding combination that we'll put clear up here, not because it's immediately clear that it should be really high in energy, but because we're going to need it later on when we mix the orbitals together to get the sigma out orbital. All right, so this would be maybe this. All right. Then what do we have left? Well, I guess you could imagine the 2px orbital on carbon overlapping with 1s orbitals on hydrogen, and you'd have a wave function change, sign change at the carbon nucleus. So something like this and that. Okay, that works all right. But then we have two other orbitals, the 2py and the 2pz orbitals, and those are both aligned 90 degrees away from the x-axis, so they cannot be they cannot interact with the hydrogens. Here is the 2pz orbital. I'm sorry, is my big head in the way? Am I blocking? Okay, I'm trying to. Somebody moved this over, and so anyway. The pz orbital would be here to our left and right. And with respect to that pz orbital, the carbon and the hydrogens are in the node, so there can be no orbital there. We would call this a non-bonding orbital because the orbital's only on one atom. And then it's kind of hard to represent, but the 2py orbital would be sort of coming out in this direction, out at us and back away from us. All right. So, and we would expect those to be sort of equal in energy. The two bonding orbitals are lower in energy, and then we'd have these two equal in energy non-bonding orbitals, and then we'd have this higher energy orbital. So let's try to follow through what happens as we go from the linear structure to the bent structure. All right. So in the bent structure, we're simply going to take both of those hydrogens and pull them back this direction. That's going to not change the lowest energy orbital a whole lot, other than, as we said before with pyramidal methyl, there might be some long range overlap with between the hydrogens, and so we might expect this to go down in energy just a little. And shall I attempt? Yeah, sure, dotted line. Okay, so not a lot of stabilization there. Let's consider what happens to our next orbital. We still have the px orbital on carbon. We still have the 1s atomic orbitals on hydrogen, but we should have not as good overlap. So based on our QMOT principles, this is going to go up in energy, and I don't know by how much, but probably by more than the lowest one goes down. Okay, so that's a destabilization upon changing geometry. But that's not the whole story. If we think about, I'm going to try to represent this y orbital just a little bit better. I'm going to have like a lobe here and a lobe back there, and the node is in the plane of the page. I hope that's close enough. So for the 2py orbital, notice that the node is the xz plane, the plane of the page. And when we go from linear to bent, those hydrogens stay in the plane of the page, and so there can still be no orbital on them. So actually the energy of that 2py orbital is unperturbed by the geometric distortion. It just sort of stays as it is. That makes sense? We're not introducing any new orbital overlap. In contrast, and here's where I'm going to need some space because I needed some room for things to be stabilized. So I'm going to cheat. I realize you can't do this in your notes, and oh well. In contrast, the 2pz orbital, once we distort from linear to bent, suddenly we introduce a new overlap that we didn't used to have. Suddenly that lobe on the back can overlap with the hydrogens. So let's represent this with pink here and here and here, and maybe yellow there. All right, so and I'm going to write this one in the middle because it's not the final orbital that we get. We have to do one more thing. But yeah, we go down, the 2pz orbital goes down a whole lot in energy because we get new overlap. Now, if you, let's see, and then this one, I'm not sure what should happen to this one. We won't necessarily worry about it other than to draw it.
Sorry, Dr. Price.
Yes, sir.
So in this case, do we still say that the 2pz and the 2py are degenerate orbitals?
Over here they are,
Okay.
and bending breaks the degeneracy. It leaves one unchanged and the other goes down. Yeah. Okay, so at this stage, questions so far about how we got there? Basically the same thing as pyramidal methyl. As we did before with pyramidal methyl, we are going to apply rule number 7. And rule number 7 is that when you have two orbitals with the same shape, but they differ in the identity of in the type of atomic orbital that's on one of the atoms, such as 2s here versus 2pz here, we mix them together to get new hybrid orbitals, as we did with for going from planar methyl to trigonal planar methyl. When we mix the 2s orbital up here with the p orbital on carbon, we're going to get a hybrid orbital out that looks like this. It's got more s character in the part of the orbital that's on carbon. Oops. So we'll draw a hybrid type orbital on carbon. Because of that increased s character, the orbital goes down in energy by some amount. I won't worry about how much. and correspondingly, this higher energy orbital would turn into something like this, and we don't actually need to worry too much about what that structure is. It's the other combination from mixing.
So in most cases, even if you ignore that one, it will be okay.
Yeah, in most cases you ignore that higher energy one, and you're fine. The only reason we're even thinking about it here is because we need it for rule number 7. That's how we get from having just a plain old p orbital here to having a more hybrid orbital. So notice the players that we're getting out of this. We're getting out a sigma CH2 kind of orbital. And if I zoom out and just look at what we had before, in shape, it's almost the same as the lowest energy for pyramidal methyl. It's just flat instead of tetrahedral. This orbital we would call a pi CH2 orbital. Its closest cousin up for pyramidal methyl would have been maybe this one, where the p orbital overlaps with a hydrogen here and the 2 hydrogens there. And then we have the sigma out, which we also made up for pyramidal methyl, and then left over is the 2py orbital that's not even changed. So we took, if you, yeah. So here are our 4 orbitals for bonding. Now, there's a couple of things we could consider here in terms of examples to sort of understand geometry. Let's think about water. Okay, water has 8 valence electrons. So we'll use the color blue for water. And let's ask, should water be linear or should water be bent? So 1, 2, 3, 4. What did I miss? Water doesn't.
It's 8.
Okay, sorry. Okay, so in the linear picture of water, we have 2 lone pairs that are equal in energy. In the bent picture of water, we have my 2 highest energy electrons are no longer equal in energy. One of them's in this sigma out and the other's in the 2py. And the relative order of these 2 doesn't really matter. So what geometry do you predict water to have, linear or bent? Bent, and of course, and so it is. Now this contrasts a little bit, this notion of your 2 highest energy electrons being in different types of orbitals contrasts with the valence bond theory picture of water, which would have had sort of, you've got 4 groups around the oxygen, so we'll call that water sp3 hybridized, and we would say 2 equivalent lone pairs, and we would say they would be in probably sp3 kind of orbitals, right? But actually, and we can formulate it that way, and frankly, it's very environment dependent. I think this picture is of a lone water molecule by itself in the gas phase. You put other water molecules nearby to interact with, and things can change. Go ahead.
Can you move that?
Yep. Thank you. Sorry. So according to this picture, you've got 2 different kinds of lone pairs on the oxygen in water. You have one that is P rich, and that's the highest energy one. And then you have another that's richer in S character. And so if you've ever been tempted to draw the lone pairs on water as these rabbit ears, they do not agree with our QMOT prediction. Now, as I said, a lot of this can change if we think about different water molecules interacting with each other, but at that point we will probably stop thinking too much about what the wave functions look like and focus on the intermolecular interactions. All right, other questions?
So instead it would look like a lone pair on top of the oxygen and then below?
Yeah, how would you draw it? I mean, drawing it this way is fine, right, for all intents and purposes. You might, though, in an acid-base reaction, have thought which of those two lone pairs is the one that does the attacking, and it's the higher energy one. Yeah. This distinction of two different lone pairs, you can almost forget about it, but it's important in analysis of protein structure, and I'll show you that later. All right, what else? I suppose we could also consider carbene structure. What is a carbene? A carbene is a carbon that's neutral but doesn't have a full octet. Okay, and these can be useful in a number of different organic reactions. Let's take the orbital picture we just did. I'm going to copy it again. I'm sorry. If you're wanting to follow along in your notes, don't worry about drawing the orbitals, just draw the lines where we have them and put the names nearby them. And for simplicity, I'm going to erase this stage in the middle. Okay. So for a carbene, we have only 6 valence electrons. So people sometimes talk about hypervalent atoms. They have more than the regular number of electrons. Maybe this is hypovalent, I don't know. But 6 valence electrons. So if we did that here, we would fill these 2, and then we would fill these 2, one with each. In contrast, if we did the bent version, we would just put those 2 highest energy electrons here. And so in the bent picture of a carbene, your electrons are in this S-rich sigma out orbital, and you've got up here, the LUMO is an empty p orbital. And in that way, you might imagine that this carbene could be both an electrophile and a nucleophile. This is a high energy lone pair, and this is a relatively low energy empty orbital. And so that has a lot to do with carbene's interesting chemistry. There's another issue here, and that has to do with spin state. Over here, overall spin equals a 0 because we have no unpaired electrons. Over here, overall spin is like 1. This is a singlet state. This is a triplet state. And based on what you see here, what do you predict is the lower energy state, singlet or triplet? Singlet, and so it is with most carbenes. There's another prediction you can make. If a carbene is triplet, what's its geometry going to be? Is it going to be bent, or should it be more towards the planar side? I'm sorry, the linear side.
Sorry, what do we mean by singlet and
triplet? Singlet and triplet are words from physical chemistry that describe whether or not you have unpaired electrons, and if they're unpaired, or their spins parallel or anti-parallel. Singlet means all of the spins match up with all of the, how do I say this? Somebody say it better than me. Every electron with alpha spin has a corresponding electron with beta spin. So there's no extra net spin. In the triplet state, you have an excess of one spin over another. Yeah.
So why did we put in the bent? Why did we put both electrons in the like sigma out instead of putting one in that and one in the 2py?
Why did we do that? Simply because of the energy difference.
Just because it's so much lower.
If you're going to be bent, it should be more stable to have the electrons here. Yeah.
In the, I think it was a chapter 14 study guide, there was a question about basically making the same prediction but based on Hund's rule.
Uh-huh.
So based on Hund's rule, we would have predicted linear, right, because of the spin pairing.
Uh-huh.
But now that we're looking at this picture, we see the energy difference.
Okay.
We can say singlet probably.
Yeah, so what the heck's going on here, right? Because what about, that's a great question, what about K? The K integral that says you get a bonus when you have parallel spins. Well, imagine some intermediate state that's not quite linear, but it's also not quite bent. Maybe the angle is not quite 180, but it's also not quite 120. You would predict that at that stage, your 2p y orbital would remain unchanged, and the 2pz orbital would go down a little bit in energy. And maybe at that stage, that combined with the extra k is enough to make the triplet state better than this one. Because you're right, this diagram does not capture that issue at all. So, and I don't know at what point and at what geometry you get to the point where the k overcomes the stabilization you get by having both of them here. I also know nothing about forbidden versus non-forbidden transitions. How do you flip the spin of something? I don't know. And if you want, you can actually go into Gaussian and do this. Make a carbene, and all you'd have to do is say you'd make a CH2 that's bent, and you'd have to say charge is 0, and its spin state is either 1 or 3. No, whatever. I mean, however you put in singlet or triplet, and you can look at the changes in the geometry. And the prediction is the triplet should be less bent than the singlet. All right, cool. All right, well, do you want to make some molecules?
Yeah.
Yes. So I want you to remember, because we could draw this out, but it would take forever. So what we're going to do is just remember the alphabet we have of group orbitals for our various structures. So remember for CH3, bent pyramidal CH3, we had a sigma CH3. We had 2 equal in energy pi CH3s that look like this. One of them involved all the hydrogens, the other involved just 2 hydrogens, and one was left out in a node. And then we had a sigma out orbital. So those are our 4 group orbitals for methyl. Similarly for CH2, you've got bent CH2, you've got a sigma, a pi, a sigma out, and then a 2py orbital. All right. So with that, I'm going to switch to Gaussian and run. All right, so here is ethane. Everybody see? Good. And I've run the calculations on ethane, and we have the molecular orbitals here. So we'll just make that full screen. This is the lowest energy valence orbital. These two come from the core 1s electrons on carbon, so we're going to ignore them. What does that look like it comes from? Of your alphabet of methyl things, what's on that list? Heather?
It's the two 1s combined ones.
down at the
Yeah,
bottom?
it's the sigma CH3, the one we get from
Yeah.
combining the 1s's on hydrogen with the 2s on carbon. We line them together in phase. We get this orbital that's delocalized over most of the molecule. It's got some CH bonding character, by which we mean there's orbital in between the two carbons, and it's got a lot of CH3 bonding character. Now remember, in MO theory, if you ask which bond does this represent, the answer is yes. It represents a part of all of those bonds if you want to transition to valence bond theory. Okay, next one. What does that look like?
Is it the sigma antibond?
Yeah, it's the same thing. It's just the out of phase combination. Yeah, so if we called this the sigma CH3 plus sigma CH3 orbital, this would be sigma CH3 minus sigma CH3. And why doesn't this show up way clear high up there? Well, the answer is that there's not a huge amount of overlap between s orbitals on each of these carbons. And so it's just as it's not that stabilizing relative to the methyls by themselves, to have the plus interaction, the minus interaction's also not that bad. Okay, next one. What does that look like it comes from? One of the pi CH3s, and it's the one that has the p orbital on the carbon, and it's overlapping in phase with the hydrogen here and with the two hydrogens on the bottom. And then you bring those together side by side, and you have something that looks an awful lot like maybe how you would have drawn a pi bonding orbital. That just blew my mind that a pi bonding orbital could be responsible for sigma bonds, right? Isn't that kind of nuts? And, you know, what about the fact that I thought that pi type orbitals were higher in energy than sigma type orbitals? Well, they are, right? Okay, this orbital has some sigma bonding character. You can see that in the sense that you've got orbitals between, orbital density between carbon and hydrogen. It's not a carbon-carbon bonding. Well, I suppose it is a pi type carbon-carbon bonding orbital, because you do have some density between the two atoms, but there also is a node in the plane of the carbons. Now, you may not be able to see the numbers, and that's just sort of, I don't think they're going to increase in size. But the orbitals 5 and 6 are actually the same in energy. And that's because they both derive from pi CH2 orbitals. This is the one we get. Do you remember there was one of the pi CH3s where a CH bond was in the plane of the node? This comes from overlap of a p orbital on carbon with one hydrogen on top and one hydrogen on the bottom. Same overall shape, also CH bonding. And because of that same overall shape, it's the same in energy as the previous one. All right, so we've accounted for the sigma plus sigma, the sigma minus sigma. One of the pi's plus pi, the other pi plus pi. We're still missing the two minus pi combinations and the sigma out combination. So sigma out comes next. And the reason this is lower than the pi plus pi, or the pi minus pi combination, is that you have direct end-on-end overlap of those two sigma out orbitals, and that's quite stabilizing. So, yeah. Then the next highest ones are, this is one of the pi CH3s minus the other, that's out of phase. Hold on, why is that a bonding orbital? This green line over here represents the space, represents a difference between a bonding orbital and an anti-bonding orbital. Down here, electrons are more stable than they would be on the separated partners, and up here they're higher than they would be. Why is this still stabilizing? Well, though it's sort of anti-bonding in between the carbons, it's still quite CH bonding. You still have overlap of a carbon and a hydrogen within the same lobe. So even though this is an out-of-phase combination, it still counts as a bonding orbital. And then we have another degenerate, same in energy 1 like you would expect. It's the same shape. It comes from overlap of the pi CH3s where one of the hydrogens is in the node. Okay. Questions so far about ethane? Yeah.
This one and the one just before, did we have was this on the example of when we did all those different energy levels, the energy diagram that we did? Are these any of the pi CH3 bonds or?
Yeah, so let me switch back to, how do I defeated you, Gaussian. I'll go ahead and switch back to, okay. And maybe the easiest thing to do is actually to grab an image from a previous version of the class. It'll be pasted in the notes. For the sake of our discussion, I don't know that it's worth drawing everything. Okay. That's why we're not going to draw it, because it's yuck. Okay. Oops. That's not. That's not really what I wanted to do. Okay, fair enough. So this was that lowest energy orbital that we get from overlap. I'm sorry, Samantha, let me back up. Your specific question was?
Just with the ones that look like anti-bonding, but they're not, how are we getting it from this diagram?
Okay, yeah, I'll show you that. So starting low, if you mix the two sigma CH3s, you get a bonding one, and the out-of-phase interaction, the minus combination. This is still a bonding orbital because you've got in-phase overlap between carbons and hydrogens, though we would say it's maybe carbon-carbon anti-bonding. Now, mixing the two pi CH2s together, these are the plus combinations. So this pi CH3 with this pi CH3 gives you this version with a lobe up here and a lobe down there and a node in the middle. This is the other one you get from combining these two pi CH3s side by side. Now, the other two are the minus combinations, and that's up here. So just as we got these from adding the two pi CH3s together, we get these two by subtracting one from the other. So zooming in to look at that, here's one of the pi CH3s, here's the other, and they're opposite in phase. But it's still a bonding orbital, because even though we would say it's carbon-carbon anti-bonding, you've still got favorable overlap in phase between carbons and hydrogens. So this is kind of like, this pi minus pi orbital is kind of like the sigma minus sigma orbital. It's anti-bonding in the carbon sense, but it's still quite CH bonding. Same thing for the other pi minus pi orbital. And then remember, our highest energy group orbitals were these sigma out orbitals, but you pair them together, and because there's such good overlap between these lobes that are pointing out to where the bond is, that goes more stable even than the two pi orbitals. Yeah?
So for
this molecule, what would the first antibonding?
What would the first antibonding orbital look like? I don't know. We could do that in Gaussian, but our group orbitals are going to be best at predicting bonding orbitals. Once you get to the antibonding orbitals, somehow some strange things start to happen that I don't understand. I just know as I've looked at antibonding orbitals in Gaussian, you can do it if you want. Sometimes there's really weird
And we don't need to know
things
these
going
things.
on. No. At most, you'd want to know what the LUMO is for molecules that are electrophiles. And since ethane's not really an electrophile, we're not going to worry about it. One interesting feature of all of this, our valence bond theory would tell us that in ethane, you've got one carbon-carbon bond and six carbon-hydrogen bonds. Now, in our QMOT picture, we can't necessarily sequester each orbital into being just carbon-hydrogen or just carbon-carbon, though we have 1, 2, 3, 4, 5, 6 orbitals that are mostly carbon-hydrogen. And then we have one, the sigma out plus sigma out, that's mostly carbon-carbon. So, valence bond theory, and as I said, the conclusions of valence bond theory are mathematically identical to those of molecular orbital theory if you do the math right. So the idea that you've got one carbon-carbon bond and 6 carbon-hydrogen bonds checks out okay, even with our MO picture. The nice thing about these group orbitals, though, is it tends to go in line with what we think about when we think about functional groups. And there's this idea in OChem that functional groups describe reactivity, and you can move one from a spot on one molecule and then another molecule that has the same functional groups, and there ought to be some similar properties. Same thing with the orbitals. There ought to be some similarities in the orbitals. Okay. Samantha, do you have a follow-up question and all of that? Okay. So I'm going to have to stitch together a lot of these ethane. I uploaded tons of molecules here because I didn't know how far we'd get. Let's look at ethylene. This you make from 2 bent CH2 groups side by side. And you construct the orbitals and fill them up with the available electrons. Again, I'm only showing you the valence orbitals. This is the one we get from side-by-side overlap of those 2 sigma orbitals, sigma CH2s. As expected, the next combination is the minus version. This is this is carbon-carbon antibonding, but it's still quite good at carbon-hydrogen bonding, so it's still a bonding orbital. Next, you would expect the pi plus pi CH2 plus pi CH2. It's exactly what you see. This is overlap of the p orbital on carbon with 1s orbitals on hydrogen. And then the other one you would expect, the other one is actually, here's the other, I'm sorry. I'm remembering, if you go back and look at your notes, that in linear or in bent CH2, we only have 4 things, right? We have the sigma CH2, the pi CH2, the sigma out, and then the p orbital. Am I right on that? Sorry, I got confused. So, sigma plus sigma, sigma minus sigma, pi plus pi. There should be a pi minus pi, and indeed there is. That's it. But it's higher in energy than the sigma out plus sigma out. And if you had to say, which bond is this associated with? Well, it's carbon-hydrogen bonding in character, but it's also looks pretty well like a carbon-carbon sigma bond. And then, what have you learned? What's the reactive part? What's the highest energy electrons in ethylene? The ones that are in the pi bond, well, it just so happens that the highest energy orbital comes from side-by-side overlap of those 2 p orbitals that were left over. Okay? And then if you want to see the LUMO of ethylene, it's the pi star, 2 pi orbitals. Two sort of p orbitals adjacent to each other and out of phase. So interestingly, when I teach sophomores in organic how to think about these molecules, I'll teach them to still think of electrons as being in the space between two atoms. I'll think of 2 electrons in a bond, but I'll also have them identify the HOMO and LUMO of the molecule. And interestingly, valence bond theory would tell you that the highest energy electrons are the pi electrons. That's what MO theory tells you too. And you can actually help students figure out HOMO and LUMO without even telling them about all of this crazy stuff going on down here, right? Because even if you wanted to consider sigma bonds as being regular the way you think about them in valence bond theory, you could come to the most sophomores know what a pi bonding orbital looks like, and some of them know what a pi star antibonding orbital looks like without even worrying about all of this. So in practice, as we talk about organic molecules, we're going to pick and choose from valence bond theory. We're going to retain some focus on carbon, hydrogen, carbon-carbon sigma bonds, but we'll also want to pay close attention to antibonding orbitals. All right, let's see. The last couple minutes, maybe I will show you. There's a bunch to show you. Maybe I'll show you chloromethane. This is you can think about this, making this by combining the group orbitals from methane with the available orbitals on chlorine, which is an s orbital and then 3 p orbitals from a different row of the periodic table, but same kind of alphabet of things we have to deal with. So let's, oh, I did all of them. No, I only did the HOMO and the LUMO. Okay, the highest energy orbital we get from overlap of one of the pi CH3s with one of the p orbitals on chlorine, and this is the out of phase combination. The LUMO, the lowest energy one, is the out of phase combination of the sigma out with one of the p orbitals on chlorine. And we could have, I didn't intend to walk through complete construction of chlorine using the group orbitals from methane and from chlorine, but you can start to make sensible predictions based on the principles that we've learned. The last one I'll show you today, and we'll come back to this next time, is formaldehyde, a bent CH2 and an oxygen. And you can go through and make those. I'll show you maybe the highest energy orbital, which is overlap of a pi CH2 with a p orbital on oxygen, and this is the minus combination. And then the LUMO is the pi star, but it's mostly on the carbon. And the reason for that is, here is the pi bond. When you make the pi bond, it's overlap of a p orbital on carbon with a p orbital on oxygen. Oxygen's lower in energy than carbon, so the bonding orbital should be mostly on oxygen. The anti-bonding orbital should be mostly on carbon, and so it is. All right, there's more to do there, and I know we've gone through that quickly, so we'll come back again next time. Have a great weekend. Try not to get COVID.